So we're continuing in section 12.4 on partial derivatives, and we're now going to be taking a look at how to find higher order derivatives, second derivatives, third derivatives, and so on. And probably unsurprisingly, the technique's not too different than it was with just single variable calculus. You just keep taking derivatives of a derivative. The only difference is, because we now usually have more than one possible variable, it's actually possible to take our second derivative, for example, with respect to x twice, y twice, or once with respect to x and once with respect to y. So we have more choices in terms of constructing these higher order derivatives. Let's take a look at example 6 to illustrate this. I've got a fairly simple function right here, and I'd like to start by finding the derivative of f with respect to x. That's going to be a 15x squared. And I'm going to start doing a bit of my arithmetic in my head here. With respect to x, that's just going to be a derivative of x is 1, so I'll just get a 7y to the 4th. And of course the derivative of the constant term would be 0. And if I now say that I want the second derivative of f, still with respect to x, notice I have f sub x here. The delta notation looks like this. And I'm just going to go back up here and take another derivative with respect to x, which would give me 30x. And that would just be a minus 0, so I won't even bother writing it down. Now another option for the second derivative would be to do f with respect to x and then y. So if I go back up to f sub x, and this time when I do another derivative, I do it with respect to y, my first term will have a derivative of 0, and the second one's going to give me a negative 28 y cubed. By the way, notice one thing here. There's sort of a reversal in notation. It's correct, but it's something to kind of keep in mind. This says do x first and then y. This says the same thing. Do x first and then y. It's that operator notation. With operator notation, we do the one closest to the f first. All right, let's do a third derivative, f sub x, x. So I'm going to go back to f sub x and just do another derivative with respect to x, giving me 30. How about f sub y? Again, start at f sub x. The derivative of that with respect to y would be 0. How about f sub xyx? Go back to f sub xy, right here, and take a third derivative with respect to x. That's constant with respect to x, so 0. And I need to swap these. Hold on to that one for a minute. We haven't done a yx first. Let's go over here instead. F sub xyy. So start with f sub xy right here, and now do the third derivative with respect to y. That would be negative 84 y squared. All right, let's start the second column. This time I'm going to start with f sub y. So going back to the beginning, f sub y, I get a 0 here. I would get a negative 28 xy cubed plus 4y. A second derivative with respect to y also. That would give me a negative 84 xy squared plus 4. How about f sub yx? Go back to f sub y and take the derivative with respect to x. That's just going to make that x a 1, right? So negative 28y cubed plus 0. F sub y. So let's see, f sub y was up here. Another derivative with respect to y. Negative 168 x y to the first. F sub yx. Back here, and then with respect to x, negative 84y squared plus 0, and f sub y xy, back here to yx, and another derivative with respect to y would be negative 84y squared. And then finally, let's come over here, f sub y xx. Start with f sub yx, which was right here, and do another derivative with respect to x. That's constant with respect to x, so I'm going to get 0. All right, whew, a lot of derivatives. Take a look at these, though, because hopefully something's kind of jumping out at you. We got the same answer a lot, didn't we? First of all, right here, notice that it didn't seem to matter whether I did first x and then y, or first y and then x. I got the same partial derivative. Again here. Notice that every single one of these derivatives had 2 x's and a y. So twice with respect to x and once with respect to y. Didn't seem to matter what order. I got 0 every time. And one more time over here. Again, all of these had 2 derivatives with respect to y, but 1 with respect to x. And the order didn't matter. I got negative 84y squared every time. Now I know that's just one example, but I am going to tell you it works every time. And if we stated that result as a theorem, it would look like the theorem at the bottom of this page. So as long as f of x and y is a continuous function, equivalent mixed partial derivatives are equal. In other words, the order in which differentiation occurs does not affect the final result. That's something that you kind of can use to help yourself, because sometimes it just looks easier to do a derivative first with respect to one variable than the other. Think about those problems like with product rules or no product rules, things like that. So if you see one and you'd rather do x first instead of y, or y first instead of x, you'd be free to do it either way. All right, we are going to wrap up this section with just one example of an application. As I had mentioned earlier, most of our application problems are actually going to come a little bit later in the chapter. But we're going to look at one rate of change problem here. In our example, body mass index, or BMI, is given by the function B equals W over h squared. W represents weight in kilograms, and h is height in meters. The first thing I'd like to do is find the rate of change of BMI with respect to weight and interpret the results. So I'm asking for a rate of change. That means I'm asking for a derivative, and specifically of BMI, B, with respect to weight, W. So I'd like the partial derivative of B with respect to W. As I look at my function, h squared is getting treated as a constant, so I could literally think of this as 1 over h squared times the derivative of W, which is 1, or just 1 over h squared. As far as interpreting the result, let's think about this for just a moment. If height is being treated as a constant, this thing is always positive, right? H squared, of course, is always a positive value, both because it's squared, but also because people can't have negative heights. Does that make sense? Well, let's see. We're talking about the rate of change with respect to weight. If your height stays the same, constant, but the weight increases, then body mass index would also increase, right? BMI would go up as you gain weight. So as weight increases, BMI also increases, which is logical. All right, what about part B? I want the rate of change of BMI here with respect to height. So partial of B with respect to h this time. And it might help me out a little bit if I rewrite that as w times h to the negative 2. By the way, using that negative exponent, when you do your classwork from this section, keep that little trick in mind. There's a problem on there that if you rewrite with negative exponents or fractional exponents, or maybe it's both, it'll save you a ton of work. So keep it in mind. I think it might be negative exponents. All right, so the partial of b with respect to h. W is a constant multiplier, so I'm just going to get negative 2w, h to the negative third, or negative 2w over h cubed. Now again, we're talking about a human being here. Weight and height are always positive values. So with that minus sign there, this is always negative. Let's see if that makes sense. What happens as height increases if weight stays constant? So think about a child who maybe is growing, getting taller, but not gaining any weight. BMI would go down, right? More height with the same weight. And again, that makes logical sense. That's why our derivative is negative. BMI is decreasing as h goes up. All right, we'll keep those in mind, and we're going to take a look at an interpretation that has to do with level curves. Remember, I mentioned to you those things would come back to haunt us a few times, and here's one of them. What you're seeing here are a couple of different views of maple graphs for the surface b equals w over h squared. I entered this into maple as x over y squared. So x corresponds to weight. So this is really the weight axis. And y corresponds to h. So this is my y-axis. This really is the h-axis. Can you visualize in your head what the level curves would look like? If you were to intersect these surfaces, or this is just one surface, multiple views, if you were to intersect this surface with a horizontal plane, a constant b or z value, what would it look like? Let's see, if you were to kind of cut through horizontally, see if I can get this to show up. You can actually see one of them right here where I cut it off, right? This would be a level curve right here, wherever I happened to cut off the z value, but there would have been more of them lower down. Okay. As a matter of fact, it looks to me like they're all kind of like square root curves or half parabola sort of shapes, and it looks like the higher up they are, or in other words, the larger the b value, the closer to the w-axis we are. So this would be a smaller b. Remember, b is like the z value on the graph. This would be a larger b. So that's what those level curves look like. And each level curve corresponds to a constant body mass index. We've graphed a few of the level curves on the next page. And you can see they look just like what we were predicting, kind of those half parabolas or square root curves, look like that. And just as predicted, the larger b values are closer to the x, so it's really the w-axis. The y is really the h-axis. All right, here's what I'd like to do. I'm going to go ahead and see if I can, well, maybe I'll have to do it as we go. Let's imagine that we're starting out somewhere. It doesn't really matter where. Let's just kind of pick a point. Let's just say right here. Okay. And let's imagine first that we gain weight while keeping our height constant. So height stays the same, horizontal, but weight's going to go up. Look at what happens to the body mass index, or the b values. As I move over, I go from my starting b, which was 21, to a larger b of 24, and then finally I'm down here to b of 27. So again, I'm seeing that as weight goes up, BMI goes up. That's exactly what we predicted based on our derivative, right? What if we go the other way? What if we keep the weight constant, but we increase the height? This way, right? Weight staying constant at around 30, but we're going up in height. Notice here we started on the b equals 21 curve, but as we go up, we're now down to the b equals 18 curve. As the height increases, the b values are going down. Again, exactly what we predicted based on our derivative. So there's just a little connection for you between what we're seeing with the derivatives and what we can also verify by looking at those level curves. All right, that brings us to the end of section 12.4.